Astronomers using two completely independent methods to measure the universe keep getting different answers. Precise instruments, careful teams, repeated tests, and the numbers refuse to agree. That disagreement has a name. Scientists call it attention. But tension is a quiet word for what it actually means. Our best model of the entire universe may be missing something fundamental. We are going to travel to the places where the cracks are showing. A cold scar in the oldest light ever measured. A void so enormous our own galaxy is falling through it right now. A structure so large it should be impossible. And a direction, a faint persistent signal suggesting the universe has a preferred axis that standard physics says should not exist. If you find the universe as unsettling and magnificent as we do, subscribing to Late Science keeps you inside every discovery as it unfolds. The edge is telling us something. We start now. There is a boundary around us that no spacecraft will ever cross, and no telescope will ever see past. It has a precise size. Everything we have ever observed, every galaxy, every signal, every particle of ancient light, exists inside a sphere roughly 93 billion light-years across. Beyond that boundary, space continues. But the information does not. This boundary exists because light travels at a fixed speed, and the universe has a finite age. The universe is approximately 13.8 billion years old. That means the oldest light reaching us has been traveling for nearly that entire time. Anything farther away than that travel distance simply has not had enough time to send us a signal. The edge of what we can observe is a wall built from time itself, not from matter or force. We call it the observable universe. And for most of cosmology's history, scientists assumed it was essentially the same in every direction. Uniform, smooth, a sphere with us near the center, surrounded by roughly the same density of matter in all directions. That assumption is baked into the standard model of cosmology. Here is the problem. The data is starting to push back against it. Several independent lines of evidence now suggest that something large is structurally different about one broad region of the sky compared to the opposite direction. Galaxies across enormous distances appear to move with a faint but measurable drift that is not fully explained by local gravity. The oldest light in existence shows temperature patterns that align in ways that seem statistically unlikely. Massive structures appear where the standard model says structures that large should barely exist. Each of these signals, taken alone, could be explained away. Scientists are careful about that. Single anomalies happen. Statistics produce outliers. But the signals are pointing in overlapping directions, and that convergence is what makes this moment in cosmology unusual. We are not floating in a uniform sphere of matter. We are embedded in something far more structured, far more directional, and possibly far more strange than the standard picture allowed. One of the most concrete examples of this is motion. Our galaxy is moving. Every galaxy moves through space due to local gravity. That much is expected. But measurements show our galaxy, along with millions of others, is being pulled toward a specific region of the sky at a speed of roughly 1.4 million miles per hour, relative to the ancient background radiation. That pull is real and measured. Its cause is only partially understood. There is a massive gravitational concentration in that direction. There is also a massive gravitational void pushing from behind. The combination of a pull from one side and a push from the other creates a kind of cosmic current, and we are caught inside it. What makes this genuinely strange is the scale. The structures generating this motion are hundreds of millions of light-years across. At that size, standard cosmological models predict the universe should be averaging out, smoothing into uniformity. Instead, it is still organized, still directional, still behaving as though something enormous shaped it or is shaping it in ways that the current model did not fully anticipate. The edge is not just a boundary of distance, it is a boundary of understanding. And the signals coming from near that boundary are telling us the universe we mapped may be missing a layer. The first crack in that map has a name most people have never heard, and it involves measuring the same thing twice and getting two answers that refuse to match. Every cosmologist working today knows the number, and the problem with it, the Hubble constant measures how fast the universe is expanding. Specifically, it tells us how quickly galaxies are moving away from us based on their distance. It is one of the most fundamental numbers in all of science because it sets the scale of the entire universe. Get it right and everything else in cosmology lines up. Get it wrong, and the model starts to fracture. We have two completely independent ways to measure it, and they disagree. The first method looks backward in time. Scientists use the cosmic microwave background radiation, the faint afterglow of the early universe, to calculate how the universe must have expanded to reach its current state. This measurement, carried out by the Planck satellite with extraordinary precision, gives a Hubble constant of approximately 67 kilometers per second per megaparsec. In plain terms, for every 3.26 million light-years of distance between us and a galaxy, that galaxy is moving away from us roughly 67 kilometers per second faster. The second method looks at the present universe directly. Scientists use a chain of distance measurements, nearby pulsing stars called Cepheid variables, to calibrate distances, then exploding stars called Type 1a supernovae to reach farther out. This method, refined over decades and anchored by the Hubble Space Telescope, gives a value closer to 73 kilometers per second per megaparsec. 67 versus 73. That sounds like a small gap. It is enormous. Both measurements have been checked, rechecked, and refined by separate research teams using different instruments. The gap has not closed. It has grown more statistically significant over time. As of the most recent analyses, the discrepancy sits at a level where the probability of it being a random statistical accident is extremely low. Cosmologists describe this level of confidence as above 5 sigma, meaning the disagreement is almost certainly real. This matters enormously. The two measurements use completely different physics. The Planck method relies on how sound waves behaved in the early universe, before atoms even formed. The supernova method relies on how light fades across billions of light-years of present-day space. If both methods are correct, and both have been validated extensively, then something in our model of the universe is wrong. Several explanations have been proposed. Some scientists suggest there may be an unknown form of energy in the early universe that slightly altered the expansion rate before atoms formed. Some suggest the dark energy driving the current expansion may be changing over time rather than staying constant. Some suggest there could be a subtle systematic error in one of the measurement chains that has not been identified yet. Each of these possibilities, if confirmed, would require revisions to the standard cosmological model that took decades to build. The James Webb Space Telescope entered this debate directly. A research team used it to independently check the Cepheid variable measurements that anchor the supernova method. The Webb data confirmed the Hubble Space Telescope's earlier results. The higher value held. The tension remained. No resolution has been reached. The gap between the two numbers is a live scientific wound, and both sides of the debate are real, credible, and serious. What makes this especially significant is that the Hubble tension is only the most famous disagreement. There is a second one, quieter but equally troubling, about how matter is distributed across the universe. And it points toward the same conclusion. The model works beautifully in some directions and breaks down in others. Our galaxy is forming, not through empty space at random, but toward a specific point in the sky at a speed most people would find difficult to picture. Roughly 1.4 million miles per hour, sustained, directional, and measurable. Astronomers first detected this motion in the 1980s, when they realized galaxies across a vast region of space were all drifting in the same direction, converging towards something enormous, hiding behind the plane of our own galaxy. They called it the Great Attractor. The problem with observing it directly is geometric. The center of our galaxy sits between us and the Great Attractor's general location. All the gas and dust concentrated along that galactic plane absorbs and scatters visible light, effectively blinding optical telescopes in that direction. For years, astronomers could detect the gravitational influence without being able to see the source. Radio waves and X-rays, which pass through that dust more easily, eventually revealed what lies behind it. A massive concentration of galaxies, called the Norma cluster, sits at the heart of the attraction zone. Beyond that sits the broader Laniakea supercluster, which our own galaxy belongs to. Laniakea spans roughly 520 million light-years and contains the mass of approximately 100 million billion stars. That number is almost impossible to hold in your mind. So think of it this way. The gravitational influence of Laniakea is so extended that it shapes the motion of every galaxy within it, including ours, across a volume of space that dwarfs any structure most people have ever heard of. But here is where it becomes stranger. The great attractor alone is not enough to explain the full motion. When astronomers mapped our velocity in detail, the gravitational mass they could account for in the Norma cluster and Laniakea came up short. Something else was contributing to the pull, and that something turned out to be the Shapley supercluster, an even larger gravitational concentration, lying roughly 650 million light-years away. Shapley is one of the most massive known structures in the observable universe. It contains thousands of galaxies packed into a region of space so dense that it contributes meaningfully to the gravitational flow of material across hundreds of millions of light-years. Studies published in the 2000s confirmed Shapley's role in pulling our local region of space forward. So we are caught in a gravitational flow involving multiple superclusters, stacked in the same broad direction, each adding its pull to the motion of everything around us. This is confirmed. It is measured in the peculiar velocities of thousands of galaxies mapped by large spectroscopic surveys. What remains less understood is whether this flow fits comfortably within the standard model's predictions for how matter should be distributed at this scale. Some studies suggest the amplitude of the flow is larger than simulations typically produce. That remains a point of genuine scientific debate. The great attractor is real, measurable, and enormous. And it is only half the story of why we are moving, because directly behind us, in the opposite direction, something equally strange is pushing. For decades, cosmologists focused on the pull, the great attractor, the Shapley supercluster, the massive gravitational concentrations drawing our galaxy cluster forward. But the full picture of our motion required something else, something that took until 2017 to map with enough precision to confirm. A void, an enormous region of space nearly emptied of galaxies, sitting on the opposite side of the sky from the great attractor. A region so underdense compared to the surrounding universe that it generates a kind of anti-gravity effect, pushing everything at its edges outward. Researchers published a study in Nature Astronomy in 2017, identifying this structure and naming it the dipole repeller. They used three-dimensional galaxy maps covering hundreds of millions of light-years to reconstruct the gravitational field around our local region of space. The analysis revealed that our galaxy's motion is shaped by both a pull from one direction and a push from the opposite one. The push side matters more than it might first seem. In a universe filled with matter, gravity pulls everything toward concentrations. A void does the opposite. The galaxies at the edge of an underdense region experience less gravitational attraction from inside the void than from the denser regions surrounding it. The net result is that they drift away from the void's center. The void effectively repels. The dipole repeller appears to be centered roughly behind us relative to our direction of motion, contributing to the same overall flow that the great attractor and Shapley supercluster generate from the front. Together, the push and the pull create the bulk flow of galaxies that astronomers have been measuring for decades. This combined picture, a repelling void behind and attracting mass ahead, fits the general structure of the cosmic web. Matter clumps along filaments and walls. Between those walls, vast empty regions form and expand. The voids grow as the denser regions pull matter away from them, and as dark energy stretches space itself. Our motion through this landscape is the direct result of where we happen to sit relative to that structure. What makes the dipole repeller specifically interesting is its scale. The void is large enough that its contribution to our local flow is comparable in magnitude to the pull from the massive structures ahead of us. That balance, a push and a pull of roughly similar strength shaping the motion of millions of galaxies, implies the void is among the larger underdense regions in our cosmic neighborhood. Whether the dipole repeller is unusual by cosmological standards remains an active area of research. Some simulations of the standard cosmological model produce voids of similar scale. Others suggest the combination of this void's size, its position, and the magnitude of the bulk flow it helps generate sits toward the edge of what the model comfortably predicts. That edge is where the questions get sharper. Because if our local region of space turns out to be measurably unusual compared to the rest of the universe, That has consequences for how we interpret nearly every cosmological measurement we make, including the Hubble constant measurements we just discussed. We are not neutral observers floating in a typical patch of cosmos. We may be sitting inside a structure that skews our view, and the case for that becomes significantly stronger when we examine what lies beneath us on an even larger scale. Imagine measuring a room's temperature from inside a freezer and using that reading to describe the average temperature of the house. The measurement would be accurate for where you are standing, but it would give you a distorted picture of the whole. Some cosmologists now think that is roughly the situation we are in. In 2013, a team of researchers analyzed galaxy counts across a broad region of sky and found that the density of galaxies around us appears lower than the cosmic average. The underdense region they identified is not a small local feature. It spans an estimated 1.8 to 2 billion light-years in diameter, making it one of the largest underdense structures ever proposed. The researchers, Keenan, Barger, and Cowie, gave it their initials, the KBC void. If confirmed at the scale proposed, the KBC void would mean our galaxy does not sit in a typical patch of the universe. We would be inside a region where matter is significantly sparser than average, surrounded by denser walls of galaxy clusters and filaments in the distance. This has a direct and measurable consequence. If the local universe around us is emptier than average, then galaxies near us would be expanding away from each other, slightly faster than galaxies in a typical region. The local gravity is weaker, so the expansion driven by dark energy meets less resistance. The result is a locally elevated measurement of the expansion rate. This is a proposed explanation for part of the Hubble tension. The argument goes that when astronomers measure the Hubble constant using nearby Cepheid variables and supernovae, they are measuring the expansion rate of the local universe, which is inflated by the void we live inside. The Planck measurement, which uses the early universe, measures the global average. The two differ because we are in an unusual spot. Whether this fully resolves the Hubble tension is contested. Some analyses suggest the KBC void could account for a meaningful fraction of the discrepancy. Others argue the void's effect is too small to close the gap entirely, and that additional physics is still required. The void itself remains somewhat controversial. Identifying underdense regions requires careful accounting for how galaxies are selected in surveys, and different teams have reached different conclusions about the precise size and depth of the underdensity. The 2023 analysis, using data from several large galaxy surveys, found supporting evidence for a significant local underdensity, though the exact boundaries remain under study. What is clear is that we cannot assume our local environment is cosmologically typical. Multiple independent lines of evidence, including galaxy counts, flow measurements, and the structure of nearby superclusters, suggest our neighborhood is genuinely unusual at a scale large enough to affect our measurements of the universe. That possibility is significant. Almost all of our most precise cosmological measurements begin with local calibrations. If the local universe is systematically different from the global average, then those calibrations carry a built-in offset. Correcting for that offset would require knowing the full three-dimensional structure of our local environment with far greater precision than we currently have. And while all of this concerns what surrounds us within a few billion light-years, the universe's anomalies stretch far beyond our neighborhood. Some of the strangest signals come from the oldest light ever measured, a map of the infant universe that should look featureless and instead hides patterns that have troubled cosmologists for 2 decades. About 380,000 years after the universe began, it cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was so hot and dense that photons, particles of light, could not travel freely. They kept colliding with the dense plasma surrounding them. The universe was opaque. When neutral atoms formed, the fog cleared. Photons streamed freely in all directions for the first time, filling all of space with light. That light has been traveling ever since, stretched by the expansion of the universe from visible light into microwave radiation. Today, we can detect it everywhere we point a sensitive enough instrument. It arrives from every direction in the sky, with a temperature of approximately 2.7 degrees above absolute zero. This is the cosmic microwave background radiation. It is the oldest electromagnetic signal we can detect, a photograph of the universe as it was. nearly 14 billion years ago. The Planck satellite, operated by the European Space Agency, maps this ancient light across the full sky with exquisite precision over several years. What it produced is the most detailed map of the early universe ever made. And that map is mostly what the standard model predicted: a nearly uniform glow with tiny temperature fluctuations, representing the small variations in density that would eventually grow into galaxies and galaxy clusters. The key word is mostly. Several features in the map do not fit the expected pattern. The temperature fluctuations at the largest scales, the broad patterns that span huge portions of the sky, appear weaker than the standard model predicts. This is called the low quadrupole problem, and it has been present since the first full sky maps were made by the WMAP satellite in the early 2000s and confirmed by Planck. More unsettling is what those large-scale patterns seem to be doing. The biggest structures in the temperature map of the ancient sky align with each other in ways that look deliberate. The two largest patterns, which should be oriented randomly relative to each other, point in roughly the same direction, and that direction also aligns with the plane of our solar system and with the direction of our motion through space. That alignment is strange for a reason that has nothing to do with local astronomy. The cosmic microwave background is a picture of the universe as it was before galaxies formed. Its patterns were set by physics operating across the entire observable universe. There is no known reason why those primordial patterns should align with the local geometry of our planetary system, or with our direction of motion. The probability of that alignment happening by random chance has been calculated repeatedly by different teams. The results vary, but most estimates place it well below 1%. Whether that reflects a genuine cosmic anomaly, a subtle systematic measurement error, or an incomplete understanding of how to extract the signal from local contamination remains an active debate. The alignment was striking enough that cosmologists gave it a nickname: the axis of evil. The name captures something real about the scientific tension involved. An alignment pointing in a preferred cosmic direction cuts against one of the foundational assumptions of standard cosmology: that the universe has no preferred axis, no special direction, no up or down at the largest scale. If the universe does have a preferred direction, even a faint one, the implications run deep. And the cold spot, a specific region of the ancient sky that amplifies all of these concerns, makes the case harder to dismiss. The standard cosmological model rests on a principle so fundamental it rarely gets discussed as an assumption. It is called the cosmological principle, and it states that the universe, on its largest scales, looks the same in every direction and from every location. No preferred axis, no special place, no direction that is meaningfully different from any other. This principle is not arbitrary. It is supported by strong evidence at many scales. Galaxy counts look roughly similar in different parts of the sky. The cosmic microwave background is extremely uniform. The expansion of the universe appears isotropic, meaning it proceeds at the same rate regardless of direction. But the alignment problem in the cosmic microwave background presses against that assumption with surprising persistence. When the Planck satellite completed its full sky temperature maps, researchers used statistical tools to separate the signal into components of different angular sizes. The largest components, called the quadrupole and octopole, represent the biggest temperature patterns across the sky. In a universe with no preferred direction, these components should be oriented randomly relative to each other. They are not. Their orientations are correlated, and they align with the ecliptic plane, the plane in which Earth orbits our star, as well as with the direction of our motion through the cosmic microwave background itself. Multiple independent research teams have confirmed this alignment exists in the data. The debate is about what it means. One possibility is contamination. Our galaxy emits microwave radiation, and separating that local emission from the ancient cosmological signal is technically demanding. Some researchers argue the alignment could be a residual artifact from imperfect foreground subtraction. The Planck team has worked to minimize this possibility and reports that the anomaly persists across different analysis methods, but the debate has not fully closed. A second possibility is that the universe genuinely has a large-scale preferred direction. This would require physics beyond the standard model. Some theoretical frameworks propose that the early universe underwent a period of expansion, called inflation, that was slightly asymmetric, leaving a faint directional imprint on the cosmic microwave background. If true, the axis of alignment would be a real physical feature of the universe, a relic of the conditions that existed in the first fractions of a second after the beginning. A third possibility is that this is a statistical anomaly, real in the data, but not physically meaningful. When you analyze a dataset as large and complex as the full-sky microwave map, unusual patterns appear by chance. The question is whether this particular alignment is unusual enough and persistent enough across multiple independent analyses to require a physical explanation. Most cosmologists treat the alignment as a genuine anomaly that has not been explained, while remaining cautious about drawing strong conclusions. It does not fit the standard model cleanly, but it has not yet produced a consensus alternative explanation. What gives the anomaly more weight is that it does not stand alone. The low quadrupole problem, the cold spot, the Hubble tension, the bulk flow of galaxies, and now this directional alignment in the oldest light in the universe, are all pointing toward the same broad concern. The universe is not as uniform as the standard model assumes, and the deviations seem to cluster around a specific direction in the sky. That direction keeps appearing in multiple independent measurements, and the structure most dramatically associated with it is also one of the most contested objects in modern cosmology. There is a region in the southern sky in the direction of the constellation Eridanus, where the ancient light of the universe runs cold. Measurably, significantly, stubbornly cold. Colder than the surrounding cosmic microwave background by approximately 70 microkelvins, which sounds tiny, but represents a statistical departure large enough to attract serious scientific attention for over 2 decades. The WMAP satellite first mapped it clearly in 2004. The Planck satellite confirmed it in greater detail. The cold spot is real in the data. What it means is still genuinely uncertain. In the standard cosmological picture, temperature variations in the ancient background radiation should follow a specific statistical distribution, driven by quantum fluctuations in the earliest moments of the universe. The cold spot is colder and larger than the standard distribution comfortably predicts. The probability of it appearing by random chance within the standard model has been estimated by multiple teams, with figures ranging from about 1 in 50 to about 1 in 2,000, depending on the statistical method used. Several explanations have been proposed. The most widely discussed physical explanation is a supervoid. If an enormous underdense region of space lies between us and the cold spot, photons from the ancient background would lose energy passing through it. In an empty region of space, the geometry of expanding space affects photons differently than in denser regions. If dark energy is accelerating the expansion of that void while the photons travel through it, the photons emerge slightly colder than they entered. This is called the integrated Sachs-Wolf effect. A research team reported in 2015 that they had identified a supervoid in the direction of the cold spot using galaxy survey data. The void they found spans approximately 1.8 billion light-years and lies at a distance of roughly 3 billion light-years from us. However, follow-up analyses found the void's size and depth insufficient to fully account for the temperature difference. The supervoid may contribute partially, but most estimates suggest it cannot be the complete explanation. Another proposal invokes cosmic texture, a type of topological defect that might have formed in the early universe if space itself underwent a phase transition. This remains theoretical and speculative, with no confirmed observational evidence beyond the cold spot itself. A more radical proposal suggests the cold spot marks the location of a collision between our universe and a neighboring one, a bubble collision in a multiverse scenario. This idea is mathematically possible in some inflationary frameworks, but is currently untestable. Most cosmologists regard it as speculative. What makes the cold spot significant in the context of this broader investigation is not any single proposed explanation. It is that the cold spot lies in a region of the sky roughly consistent with the directional pattern seen in the alignment anomaly. It represents another data point clustering around the same broad concern, that the universe seen from our position shows structured, directional features at the largest accessible scales. The cold spot has not been explained by the standard model. It has not been dismissed as an artifact. It sits in the data, confirmed by 2 independent satellite missions, and continues to generate research. That matters, because the anomalies at the edge of our map are multiplying, and some of the structures in the universe are so large they should be impossible by the same model that struggles to explain the cold spot. The universe has a speed limit for structure. Gravity pulls matter together, but it takes time to work. The universe is approximately 13.8 billion years old, and for much of that time it was expanding so rapidly that gravity could only pull matter together within limits. There is a theoretical maximum size for a connected gravitational structure that could form within the age of the universe. Most cosmologists place that limit at roughly 1.2 billion light-years. The Hercules Corona Borealis Great Wall appears to be around 10 billion light-years across. This structure was identified through the clustering of gamma-ray bursts, extremely energetic explosions that occur when massive stars collapse or neutron stars merge. Gamma-ray bursts are visible across enormous distances, making them useful as tracers of where matter concentrates across the observable universe. A research team, analyzing burst distributions, published findings in 2014, reporting an unusual cluster of events spanning a region of sky that at the distances involved corresponds to a structure roughly 10 billion light-years in its longest dimension. A structure that large cannot have assembled under gravity in the time the universe has existed. The standard model predicts no structure beyond the theoretical limit of about 1.2 billion light-years should exist as a single connected gravitational entity. It is critical to be precise here, because this structure is genuinely contested. Gamma-ray burst samples are statistically limited. Identifying a true large-scale structure from burst clustering requires ruling out random fluctuations in what is still a relatively small dataset. Some analyses have questioned whether the apparent clustering is statistically significant enough to confirm a physically connected structure, or whether it represents a chance alignment of bursts across different cosmic distances. The team that identified it has maintained their findings through follow-up analyses, and the structure appears in their data with statistical significance they describe as above 5 sigma. Independent verification, using larger datasets, as more gamma-ray burst observations accumulate, remains ongoing. If the Hercules Corona Borealis Great Wall is real as a connected structure, it violates a principle called the end of greatness. This is the scale at which the universe was expected to become statistically uniform, where no individual structure would dominate the view, and matter would be spread in a roughly even cosmic foam. The end of greatness was estimated to sit around 300 to 400 million light-years. Structures at 1 billion light-years were already pushing that boundary. A confirmed structure at 10 billion light-years would not merely stretch the principle, it would break it. Several other large structures discovered in recent decades, including the Sloan Great Wall and the Giant Arc, have already raised questions about whether the cosmological principle holds at the scales where we are now able to map the universe. Each new survey pushes deeper and finds structures that sit at or beyond the model's predicted limits. The universe at its largest scales is more organized, more structured, and more extreme than the standard model was built to accommodate. And that organization itself points to a deeper question: what shaped it? The answer involves a type of energy we cannot directly observe, a force that has been governing the fate of the universe since long before galaxies formed, and whose behavior at the edge of the observable universe has just started sending us signals we were not expecting. Between the walls and filaments of galaxies, the universe is mostly empty, genuinely, profoundly empty. The regions between galaxy clusters and superclusters contain almost no matter at all, at least compared to the dense structures surrounding them. These regions are called cosmic voids, and they are not passive gaps in the cosmic web. They are active participants in the evolution of the universe, expanding outward, pushing matter ahead of them, and shaping the largest structures in existence. Voids form because matter is not distributed perfectly evenly. In the early universe, slight overdensities attracted more matter through gravity, growing into filaments and sheets. The surrounding regions, slightly less dense to begin with, lost more and more matter to those growing overdensities. Over billions of years, vast regions became increasingly emptied, hollowed out by the outward migration of matter toward the denser walls. Inside a void, dark energy dominates almost completely. There is so little matter that its gravitational influence is minimal, leaving the accelerating expansion of space essentially unopposed. Voids expand faster than the average expansion rate of the universe. Their interiors grow, while their walls accumulate more material pushed outward from within. This behavior makes voids a valuable cosmological tool. Because they are so sensitive to the balance between dark energy and gravity, their sizes and growth rates encode precise information about both. Measuring void statistics across large galaxy surveys gives cosmologists an independent way to probe the properties of dark energy, separate from supernovae or the cosmic microwave background. The largest known voids in the observable universe span hundreds of millions of light-years. The Boötis void, discovered in 1981, and one of the most studied, measures roughly 330 million light-years across. When it was first mapped, it contained only a handful of known galaxies across a region of space that, by the density of the surrounding universe, should have held thousands. Follow-up surveys found more galaxies within it than the initial count, but it remains one of the most dramatically underdense regions in the nearby universe. Voids at this scale create measurable gravitational effects on light passing through them. The integrated Sachs-Wolf effect, the same mechanism proposed to explain part of the cold spot, operates here. As photons travel through an expanding void, they lose a small amount of energy. Mapping this energy loss across large areas of sky and correlating it with the positions of known voids has provided evidence for dark energy's role in driving void expansion. Several research teams have detected this signal, adding to the evidence that dark energy is real and active. The overall structure that voids create, the cosmic web of filaments, sheets, clusters, and empty bubbles, is itself one of the most visually striking patterns in nature. Seen at large scales, it resembles a foam or a biological cell structure, with matter concentrated on the boundaries between enormous spherical voids. What remains unsettled is whether the statistical distribution of void sizes fully matches the standard model's predictions. Some analyses find voids that are slightly larger or more numerous at certain scales than simulations produce. These discrepancies are small and not definitive, but they are consistent with a pattern of mild tension between observations and predictions that runs through this entire investigation. And the deepest example of that tension, a void so enormous it may encompass the entire region of space from which we make our measurements, points to a possibility that challenges how we interpret every cosmological dataset we have ever produced. In 1981, a team of astronomers mapping the distribution of galaxies in a patch of sky found a gap, not a small gap or a slight underdensity, but a region of space that appeared almost completely empty across an angular area large enough to be startling. When they calculated the distance and size of what they had found, the result was a roughly spherical region approximately 330 million light-years across, containing only a handful of galaxies where the surrounding universe's density would predict thousands. The Boötis void became one of the most discussed structures in cosmological surveys for the following decades. Follow-up observations over the years found additional galaxies within the Boötis void, including a small chain of galaxies that appears to run through its interior. The total galaxy count inside is now estimated at around 60, far below what would be expected in an equivalently sized region elsewhere. The interior is genuinely measurably underdense. Structures like the Boötis void form through the same gravitational processes that build filaments and sheets. As gravity pulls matter toward denser concentrations, the regions between them become depleted. Over billions of years, that depletion compounds. The Boötis void is old enough that this process has had substantial time to run. It sits at a distance of roughly 700 million light-years from us, meaning we are seeing it as it existed roughly 700 million years ago. What makes it useful beyond its visual impressiveness is what voids of this scale reveal about the rate and character of structure formation. In the standard model, the growth of structures, including the emptying of voids, is driven by the interplay of gravity pulling matter together and the expansion of space pushing things apart. The sizes and depths of large voids reflect how these two forces balanced over cosmic history. The Boötis void sits near the boundary of what standard models predict for void sizes in the nearby universe. Some analyses describe it as unusual, but within the range of statistical possibility given the volume of universe we can survey. Others note that combining its size, depth, and the relative absence of substructure within it pushes it toward the less probable end of expectations. One of the persistent questions about the Boötes void is whether it is a single connected void or a merging assembly of smaller voids that happen to be adjacent. The cosmic web naturally produces void hierarchies, where smaller voids cluster together along the same underdense region. Some analyses support the interpretation that the Boötes void is actually a compound structure. Others find it consistent with a single, large void. Either way, its scale reveals something important about the texture of the universe at these distances. The cosmic web is not just made of filaments and clusters. It is equally defined by what is absent. The empty regions are as structured, as gravitationally active, and as cosmologically significant as the dense walls surrounding them. And if our own galaxy sits inside a supervoid of comparable or greater scale, as the KBC void evidence suggests, then the Boötes void offers a glimpse of what our own neighborhood might look like from the outside. A vast, near-empty region, hemmed in by distant walls of galaxies, with a lone observer inside wondering whether their measurements of the universe are telling them about the whole cosmos, or just about the unusual corner they happen to occupy. That question of our cosmic address connects directly to a second major tension in the Standard Model, one that involves how clumped and structured the universe's matter actually is, and how much its observed clumpiness disagrees with what the ancient light predicted. The cosmic microwave background encodes a prediction. It tells us, with remarkable precision, how matter in the universe should be distributed today. The temperature fluctuations in the ancient light reflect the density variations of the early universe, and from those initial conditions, the Standard Model calculates how gravity would have pulled matter together over 13 billion years, producing the galaxies, clusters, and filaments we see now. The prediction is specific. The Standard Model outputs a number called S8, which captures how clumped and structured matter is across large scales. A higher S8 means the universe is more structured, more organized into dense concentrations. A lower S8 means matter is spread more smoothly. The Planck satellite measured the early universe and, through the Standard Model, predicts a specific S8 value for today. When astronomers go out and directly measure how clumped matter is today, using techniques like weak gravitational lensing, the number they get is consistently lower than Planck predicts. Weak gravitational lensing works by measuring how the gravity of matter bends the light from distant galaxies. When we look at millions of galaxies, their shapes are faintly distorted by all the matter lying between them and us. By statistically analyzing those distortions across enormous survey areas, astronomers can reconstruct the distribution of matter, including dark matter, across large volumes of space. Several independent surveys, including the Kilo Degree Survey, the Dark Energy Survey, and the Hyper-Suprime CAM Survey, have all produced S8 measurements lower than the Planck prediction. The discrepancy sits at roughly 2 to 3 sigma, which is less statistically extreme than the Hubble tension, but is consistent enough across multiple independent surveys to be taken seriously. Two tensions, two independent types of measurement, both pointing in the same direction. The real universe appears to be slightly less organized, slightly smoother at large scales, than the Standard Model built from the early universe predicts it should be. These tensions could have separate explanations, or they could share a root cause. One possibility is that dark energy is not a fixed constant, but evolves over time, behaving differently in the early universe than it does today. A dark energy that changes could alter the growth of structure in ways that shift the S8 value. Another possibility involves dark matter behaving differently from the simplest models, perhaps interacting slightly with radiation in ways that slow the growth of structure. A third possibility, and one that has gained attention, is that the early universe measurement itself is slightly off, because our position inside an underdense region introduces a subtle bias. If the local universe is genuinely less dense than average, then locally calibrated measurements feed that underdensity into the analysis without correction, pulling results away from the true global values. None of these explanations has been confirmed. All of them are active areas of investigation. What is confirmed is that the S8 tension is real, reproducible, and growing more statistically precise as survey data improves. Combined with the Hubble tension and the alignment anomalies in the cosmic microwave background, it paints a consistent picture of a model under pressure from multiple independent directions. And while these tensions involve things we can measure, There is a class of signals arriving from the most extreme distances in the observable universe that carries its own layer of mystery, signals so brief and so energetic that their source remained debated for years after their discovery. For roughly 4 milliseconds, a beam of radio energy arrives from somewhere across the universe, carrying more power than our star releases in 3 days. Then, silence. The entire event is over before you could snap your fingers. These events are called fast radio bursts, and they represent one of the most energetic and least understood phenomena in modern astrophysics. The first confirmed fast radio burst was identified in archived radio telescope data in 2007 by a team analyzing observations from the Parkes Radio Telescope in Australia. The signal had actually been recorded in 2001. It showed a characteristic sweep of frequencies, higher frequencies arriving before lower ones, consistent with the signal having traveled through enormous amounts of intergalactic plasma. The amount of dispersion in the signal implied it had traveled across cosmological distances, billions of light years. Since then, hundreds of fast radio bursts have been detected and catalogued, many by the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, which became operational in 2018 and dramatically increased the detection rate. CHIME has detected thousands of bursts, transforming fast radio burst research from a field struggling with small samples into one with statistical richness. Most fast radio bursts appear once and never repeat. A subset have been observed to repeat, sometimes in patterns suggesting a cycle, sometimes apparently random. The repeating bursts are especially useful because they allow astronomers to point other telescopes at the same location and study the source over time. The confirmed sources of fast radio bursts include magnetars, a type of neutron star with an extraordinarily powerful magnetic field. In 2020, a magnetar in our own galaxy, called SGR 1935 plus 2150, produced a fast radio burst that was detected by multiple observatories simultaneously. This was the first fast radio burst with a confirmed galactic source, and strongly supports magnetars as at least one mechanism behind these events. Whether all fast radio bursts come from magnetars remains an open question. Some properties of the detected bursts, including the diversity in their dispersion measures, temporal structures, and repeat behaviors, leave open the possibility that multiple source types are involved. What makes fast radio bursts cosmologically significant, beyond their extraordinary energy, is their use as probes of intergalactic space. As a burst travels across billions of light years, the plasma between galaxies disperses its radio frequencies in a measurable way. By analyzing how much dispersion occurred and knowing the burst's host galaxy and distance, astronomers can calculate how much ionized gas the signal passed through. This provides a direct measurement of the density of ordinary matter in intergalactic space. Results from this technique have provided evidence that the density of matter between galaxies is consistent with theoretical predictions about where ordinary matter resides in the universe, resolving what was previously called the missing baryon problem. This is a genuine success of the fast radio burst method. The edge of the observable universe is not silent. It sends us brief, violent signals, encoded with information about everything they passed through on the way here. Each burst is a data packet from across cosmic time, and as CHIME and future facilities continue cataloging them, they become one of our sharpest tools for probing the structure of the universe at the largest scales. But the deepest structural signal from the universe's history was not written in radio waves. It was written in the spacing of galaxies themselves, a frozen pattern from an era when the universe rang like a bell. In the first 380,000 years of the universe, space was filled with a dense, hot plasma. Protons, electrons, and photons moved together in a single coupled fluid, and the slight overdensities scattered across this fluid set off pressure waves, ripples of compression, and rarefaction spreading outward at roughly half the speed of light. The early universe was ringing. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, the plasma became transparent, and the pressure waves stopped abruptly. The photons decoupled and streamed free as the cosmic microwave background. The sound waves froze in place, leaving a permanent imprint on the distribution of matter. That frozen imprint is called the baryon acoustic oscillation signal. It shows up as a slight but measurable preference for galaxies to be separated from each other by a specific distance, approximately 490 million light-years. If you take any galaxy and count the number of other galaxies at various distances from it, you find a small but real excess at that particular distance. The ring of that ancient sound wave is still visible today, encoded in the positions of galaxies across the observable universe. This feature is one of the most powerful tools in cosmology, for two reasons. First, the physical size of the sound horizon, that 490 million light-year scale, was set by well-understood physics of the early universe. We know what size it should be. By measuring how large it appears in galaxy surveys at different distances, we can calculate how much the universe has expanded between those distances and the present. This gives an independent measurement of the expansion history, including the Hubble constant. Second, because the same acoustic signature also appears in the cosmic microwave background as a specific pattern in the temperature fluctuations, we can cross-check the two measurements. The standard model predicts the same physics governs both, so they should agree. Multiple large galaxy surveys have measured the baryon acoustic oscillation signal across different cosmic epochs. The Sloan Digital Sky Survey, the Dark Energy Survey, and the more recent Dark Energy Spectroscopic Instrument Survey have all produced detections. The signal is robust. The scale it imprints is consistent with theoretical predictions. Where tension enters is in what the baryon acoustic oscillation measurements imply for the Hubble constant. When analyzed within the standard cosmological model, the baryon acoustic oscillation signal from galaxy surveys tends to favor a lower expansion rate, closer to the Planck value of 67, rather than the supernova calibrated value of 73. This alignment makes the Hubble tension more structurally complex. The higher value comes from distance measurements anchored in the local universe. The lower value comes from measurements of the early universe and the large-scale structure it produced. The dividing line between these two regimes is not arbitrary. It may reflect a real difference in how the universe behaved at different epochs. Some theoretical models attempt to resolve this by modifying what happens around the time of recombination, the moment the plasma cleared. If an unknown energy component was briefly present in the early universe, it would have altered the sound horizon size. A smaller sound horizon would make the baryon acoustic oscillation ruler shorter, which would shift the inferred Hubble constant upward toward the local value. This proposal is called early dark energy, and it remains speculative. Observations have constrained how much of this energy could have existed. The window for it is narrow, and most current data does not strongly support it. But the search continues, because the baryon acoustic oscillation measurements are precise enough that a confirmed solution would tell us something fundamental about the universe's first moments. What the early universe's sound wave gives us, precisely and reproducibly, is a ruler. And the universe's ruler is currently disagreeing with our tape measure. That disagreement is real, persistent, and pointing towards something we have not yet fully identified in the physics of darkness itself. In 1998, two independent research teams studying distant exploding stars reached the same unexpected conclusion. The universe is expanding, and the expansion is accelerating. Distant galaxies are moving away from each other faster over time, not slower. Gravity should be slowing that expansion down. Something else is pushing back. That something else acquired a name: dark energy. It represents approximately 68% of the total energy content of the universe. It does not cluster like matter. It does not dilute as space expands. It fills every cubic inch of space uniformly and exerts a pressure that acts against gravity across cosmic scales. The observational evidence for dark energy is strong. Type-year supernovae, which can be used as standardizable distance markers because their peak brightness is related to their duration, revealed that supernovae at large distances were fainter than expected. The simplest explanation, confirmed by subsequent observations across multiple independent methods, is that those distant supernovae are farther away than a non-accelerating universe would predict. Space between us and them expanded faster than it would if only gravity were operating. The baryon acoustic oscillation measurements, the cosmic microwave background analysis, and galaxy cluster counts all independently support the existence of dark energy and point to a universe where it currently dominates the energy budget. What remains completely unknown is what dark energy actually is. The simplest description treats it as a property of space itself. Empty space has an intrinsic energy density called the cosmological constant, which Einstein originally introduced and later removed from his equations. Observations suggest that this constant is real and has a specific value. Every cubic meter of space contains a fixed amount of dark energy. As the universe expands and creates more space, total dark energy increases, which is why the expansion accelerates over time. The problem is that when physicists try to calculate what the cosmological constant should be from quantum field theory, the answer is catastrophically wrong. Quantum mechanics predicts that empty space should be seething with virtual particles popping in and out of existence, generating an enormous energy density. The calculated value is somewhere between 10 to the power 50 and 10 to the power of 120 times larger than the observed value, depending on the approach. This is the cosmological constant problem, and it is one of the most severe mismatches between theory and observation in all of science. Some physicists propose that dark energy might not be a fixed constant, but a dynamic field that changes over time, called quintessence. A field that varies could explain why the observed dark energy density is so much smaller than naively predicted. If the field is currently near a very flat portion of its energy landscape, its contribution would be minimal compared to the enormous values quantum theory suggests in its most energetic states. Whether dark energy is constant or evolving is now an active observational question, and recent data has raised the stakes considerably. Because the Dark Energy Spectroscopic Instrument, the most powerful galaxy survey instrument ever built for this purpose, has now produced its first major results, and the data suggests dark energy may be doing something unexpected. In April 2024, the Dark Energy Spectroscopic Instrument Collaboration released results from its first year of data. The instrument, mounted on a telescope at the Kitt Peak National Observatory in Arizona, is designed to map the three-dimensional positions of tens of millions of galaxies and quasars across a significant fraction of the observable universe. Its primary goal is to measure the baryon acoustic oscillation signal at multiple cosmic epochs and track how the universe's expansion rate changed over time. The first-year results covered approximately 6 million galaxies and quasars spanning a range of cosmic distances. When the team analyzed the expansion history encoded in these measurements, they found a potential deviation from the simplest dark energy model. The standard model treats dark energy as a cosmological constant, meaning its strength does not change over time. The Dark Energy Spectroscopic Instrument data, when analyzed using a parameterization that allows dark energy's strength to vary, showed a preference for a model where dark energy's influence was different in the earlier universe than it is today. The statistical significance of this deviation sits at approximately 2 to 3 sigma. This is below the 5 sigma threshold that physicists generally require to claim a discovery. The team was explicit about this in their published results. The deviation is intriguing, but does not constitute a confirmed detection of evolving dark energy. It requires more data. The second-year data release, expected to cover a substantially larger sample, will test whether this signal strengthens or fades. If it strengthens toward 5 sigma or beyond, it would represent a discovery of profound importance, proof that dark energy is a dynamic component of the universe, rather than a fixed property of space. A dynamically evolving dark energy would have significant implications across cosmology. It would mean the history of the universe's expansion cannot be calculated by simply applying a constant to Einstein's equations. The expansion history would depend on how the dark energy field evolved, which in turn would affect calculations of cosmic age, the growth of structures, the baryon acoustic oscillation signal, and potentially the Hubble constant. This connection is why some researchers are cautiously excited. A dynamically evolving dark energy could, in principle, affect different cosmic epochs differently, and that difference might be part of what produces the Hubble tension. The two major cracks in the standard model could share a common cause. Independent evidence for dark energy evolution has been reported by other groups. A combined analysis using dark energy survey supernova data, alongside baryon acoustic oscillation and cosmic microwave background measurements, also showed mild preference for evolving dark energy at a similar significance level, announced around the same time as the dark energy spectroscopic instrument results. The consistency between independent instruments and methods adds weight to the signal, even though neither result alone crosses the discovery threshold. What the scientific community is now watching carefully is convergence. As additional data accumulates from the dark energy spectroscopic instrument, the Vera Rubin Observatory's upcoming legacy survey of space and time, and the Euclid Space Telescope, which began operations in 2023, the statistical picture will sharpen. If dark energy is evolving, the universe is stranger than the standard model assumed, and the fate of everything, including the rate at which galaxies eventually drift beyond each other's reach, would need to be recalculated from the beginning, and the consequences of that recalculation, played out across trillions of years, lead to a scenario far more extreme than anything the current standard model predicts. The standard model of cosmology predicts that the universe's expansion will continue forever, but gradually slow in its acceleration over time. Galaxies will drift apart. Eventually, over timescales incomprehensibly longer than the current age of the universe, even gravitationally bound systems will feel the tug of expansion. But the prediction within the simplest framework, the cosmological constant model, is that expansion stays steady enough to allow galaxies, star systems, and even atoms to remain gravitationally or electromagnetically bound indefinitely. If dark energy is evolving, and specifically if it is growing stronger over time, that prediction changes dramatically. A theoretical framework called phantom dark energy describes a scenario where dark energy's density does not stay constant, but increases as the universe expands. In a universe filled with phantom dark energy, the expansion rate does not merely continue, it accelerates more and more rapidly over time. The acceleration compounds. Eventually, the force driving expansion becomes strong enough to tear apart structures that gravity and electromagnetism currently hold together. The sequence would proceed in a specific order determined by the binding strength of different structures. First, the largest, most loosely bound structures would be pulled apart by the increasing expansion rate. Galaxy clusters, held together by gravity across millions of light years, would begin to disperse. This would happen on a timescale of billions of years before the final moment. As expansion continued to accelerate, our own galaxy would be torn apart. The gravitational binding of a galaxy, enormous by human standards, would eventually be overwhelmed by an expansion rate growing without limit. Star systems would follow. Stars would lose their planets. Planets would be torn from orbits, and then torn apart themselves. In the final moments before the singularity that physicists call the Big Rip, the remaining intact structures would be atomic. Atoms stay together through electromagnetic forces, which are far stronger than gravity across short distances. But in phantom dark energy scenarios, even electromagnetic forces eventually fail. Atoms would be torn apart. The protons and electrons composing them would separate. Space itself would expand faster than the fundamental forces holding matter together could operate. The Big Rip is a legitimate theoretical prediction within specific dark energy models. The key parameter governing whether it occurs is called the dark energy equation of state, represented as W. The cosmological constant corresponds to W equal to -1. Phantom dark energy requires W to be more negative than -1. The current data from the Dark Energy Spectroscopic Instrument and other surveys does not confirm W is more negative than -1. The measurements are consistent with the cosmological constant in most analyses, with the hints of evolution sitting in a range that does not conclusively require phantom behavior. The Big Rip remains a theoretical possibility, not a confirmed trajectory. What the current data does establish is that we do not yet know the precise value of W or whether it is constant. That uncertainty has real consequences. The fate of the universe, whether it expands gently forever, accelerates into a rip, or eventually reverses, depends on a parameter we have not pinned down. This is the edge of what our measurements can currently tell us. A universe governed by an energy we cannot directly detect, whose strength we cannot precisely measure, whose future behavior we cannot predict. The signals from the edge of the observable universe are converging on this uncertainty, and the tools being built to resolve it represent some of the most ambitious observational projects in human history. The James Webb Space Telescope, was designed to see the first light in the universe. Its primary mirror, nearly 22 feet across, and its position a million miles from Earth, allow it to detect infrared light from objects so distant that the universe was only a few 100 million years old when that light began its journey. The expectation, built from decades of galaxy formation theory, was that the earliest galaxies would be small, dim, irregular, and primitive. Gravity had barely begun its work. Structure needed time to grow. The first deep field images from Webb overturned that expectation with unusual speed. Researchers analyzing Webb's early data identified galaxies at redshifts corresponding to the universe being only 300 to 700 million years old, and those galaxies were massive. Some appeared to contain as many stars as our own galaxy contains today, structured and bright, far more developed than the standard model predicted for that epoch. One analysis published in 2023 identified candidate galaxies so massive for their cosmic age that the authors described them as potentially in tension with the standard cosmological model. These findings generated immediate scientific debate. Several explanations have been proposed that do not require abandoning the standard model. One possibility is that the initial mass estimates were too high. Estimating the stellar mass of a distant galaxy from its light alone involves assumptions about the types of stars it contains, how old they are, and how much light is obscured by dust. If early galaxies had unusual stellar populations, younger and hotter stars that emit more light per unit of mass, their masses would be overestimated from brightness alone. A second possibility involves active galactic nuclei. If the cores of these early galaxies hosted actively feeding supermassive black holes, those nuclei would contribute enormous luminosity. Part of what appeared to be stellar mass might actually be radiation from the central black hole region, inflating the apparent mass estimate. A third possibility, more significant if confirmed, is that galaxy formation in the early universe was more efficient than the standard model calculates. Star formation rates in the first few 100 million years may have converted gas into stars faster than current simulations produce, building massive galaxies earlier than predicted. The scientific community has not reached consensus on which explanation dominates. Some of the most extreme early mass estimates have been revised downward as more detailed spectroscopic data became available. Webb's spectrograph can measure the precise redshifts and chemical compositions of these galaxies, providing far more reliable mass estimates than photometry alone. As spectroscopic data accumulates on the most extreme candidates, the picture is becoming more refined. What remains is a real observational challenge to the standard model's galaxy formation timeline. Even with revised estimates, a meaningful number of early galaxies appear more massive and more structured than simulations comfortably reproduce at those epochs. Whether this reflects missing physics in the models, unexpected efficiency in early star formation, or a genuine crack in the timeline of the standard cosmological framework is still being worked out. Webb is also contributing directly to the Hubble tension debate. Its measurements of Cepheid variable stars in nearby galaxies, used to calibrate the cosmic distance ladder, confirmed the higher expansion rate measured by the Hubble Space Telescope. The tension held. The tool designed to resolve the disagreement sharpened it instead. The universe's oldest observable structures are pushing back against the model built to describe them. And the mystery of what drives structure formation, what dark matter actually is, deepens with every new image Webb returns from the edge of cosmic time. Every visible galaxy, every cluster, every filament in the cosmic web sits inside a structure made of something that emits no light, absorbs no light, and interacts with ordinary matter only through gravity. Remove it, and the universe as we observe it becomes impossible to explain. Galaxies would not hold together at the speeds they rotate. The cosmic web would not have formed in the time the universe has existed. The baryon acoustic oscillation signal would have a different shape. The gravitational lensing of distant light would not match observations. Dark matter is not a speculation, it is a requirement. The evidence for its existence is independent, cross-checked, and robust across scales ranging from individual galaxies to the large-scale structure of the entire observable universe. The clearest early evidence came from galaxy rotation curves. Stars in the outer regions of spiral galaxies orbit the galactic center at speeds far higher than the visible mass can account for. If only the stars and gas we can see contributed to gravity, Stars at the outskirts should orbit slowly. They do not. They orbit at roughly the same speed as stars, much closer to the center, implying a massive invisible halo extending far beyond the visible disk. Vera Rubin and her collaborators produced systematic evidence for this in spiral galaxies across the 1970s, and the finding has been reproduced in thousands of galaxies since. The bullet cluster provided a different class of evidence. This system formed when two galaxy clusters collided. The hot gas in each cluster, which makes up most of the ordinary matter and emits X-rays, slowed dramatically during the collision due to electromagnetic interactions. The dark matter, interacting only gravitationally, passed through without slowing. By mapping the gravitational lensing of background galaxies, astronomers could locate where the mass was concentrated. After the collision, the mass was centered on the two dark matter halos, not on the hot gas. The dark matter and the ordinary matter had separated. Despite the strength of this evidence, no one has directly detected a dark matter particle. Decades of experiments designed to capture dark matter interactions, including underground detectors filled with xenon or germanium, particle accelerators searching for new particles, and space telescopes hunting for dark matter annihilation signals, have returned no confirmed detection. The most popular theoretical candidates, weakly interacting massive particles, have been progressively ruled out across a wide range of masses and interaction strengths. The allowed parameter space has shrunk considerably. Other candidates, including axions, sterile neutrinos, and primordial black holes, remain viable in various mass ranges. The absence of a detection does not mean dark matter is wrong. It means our models of what dark matter is may be incorrect, even if dark matter itself is real. The gravitational evidence remains. Alternatives to dark matter, including modified gravity theories, have difficulty reproducing all of the observational evidence simultaneously, particularly the separation seen in the bullet cluster and the precise structure of the cosmic microwave background. Dark matter shapes the universe at every scale. The tension in cosmology is not about whether it exists, but about what it is made of. And that uncertainty carries its own implications, because some proposed dark matter properties affect the growth of structure in ways that connect directly to the S8 tension we examined earlier. What dark matter is made of, and how dark energy behaves, are the two largest open questions in cosmology. They are also connected in ways that point toward the deepest crack in the standard model yet. There is a number at the center of cosmology, small but profoundly important, and our best physical theory predicts it should be enormous. The mismatch between the prediction and the observation is so extreme that physicists often describe it as the worst failed prediction in the history of science. The number is the energy density of dark energy, or the cosmological constant. Measurements from supernovae, the cosmic microwave background, and large-scale structure surveys pin it at a specific, tiny value. Every cubic meter of space contains roughly 6 times 10 to the negative 27th kilograms worth of dark energy. Incredibly small. Quantum field theory, the framework that describes the behavior of particles and forces with extraordinary precision across every other application, predicts that empty space should contain enormous energy. Virtual particles constantly appear and disappear in the vacuum, according to quantum mechanics, and this activity generates what physicists call zero-point energy. When you calculate what the cosmological constant should be from quantum field theory, the answer comes out somewhere between 10 to the power of 50 and 10 to the power of 120 times larger than the observed value. That upper estimate means the theoretical prediction is larger than the observation, by more than 120 zeros. For context, the total number of atoms in the observable universe is roughly 10 to the power of 80. The mismatch dwarfs that. No other prediction in physics is wrong by anything close to this margin. The theory is precise and successful in every domain except this one, where it fails catastrophically. Several approaches have been proposed to address this. One involves supersymmetry, a theoretical framework in which every particle has a partner particle. In a perfectly supersymmetric universe, contributions from particles and their partners would cancel out, reducing the vacuum energy to zero. Reality is not perfectly supersymmetric. so the cancellation is imperfect. But if supersymmetry is nearly correct, it might produce a much smaller residual vacuum energy, closer to the observed value. However, experiments at the Large Hadron Collider have found no evidence for supersymmetric particles at the mass ranges where they were most expected. Another approach is the anthropic argument, associated with the string theory landscape. In this framework, the cosmological constant takes different values in different regions of a vast multiverse. Most values are too large for structure to form. Only in regions where the cosmological constant happens to be small can galaxies, stars, and observers exist. We observe a small value because a larger value would have prevented our existence. This argument is logically coherent, but is not a physical explanation in the traditional sense, and it provides no new testable predictions. What this problem reveals is a deep incompatibility at the foundations of physics. General relativity, which governs gravity and the large-scale structure of spacetime, and quantum field theory, which governs particle physics, produce contradictory answers when applied to the same question about the energy of empty space. Resolving this contradiction would require a unified theory of quantum gravity, which does not yet exist. The cosmological constant problem sits at the boundary between what we can observe and what we cannot explain. And at the edge of the observable universe, the conditions approach those where only a theory of quantum gravity would apply. The observable universe has a physical boundary approximately 46 billion light-years away in every direction. Beyond that boundary, space continues. The universe, as far as physics can determine, extends further, possibly infinitely. The edge we can observe is not a wall where space ends. It is the farthest distance from which any information has had time to reach us since the universe began. That distinction matters enormously. The boundary exists because of the relationship between the speed of light, the age of the universe, and the expansion of space. Light travels at approximately 186,000 miles per second. The universe has been expanding for roughly 13.8 billion years. But because space itself expanded during that time, the matter that emitted the oldest light we can detect has since moved much farther from us than the 13.8 billion light-years the light itself traveled. The current distance to that matter is approximately 46 billion light-years. Everything beyond that distance emitted light before the universe was old enough for any signal to bridge the gap. Those regions exist, but they are causally disconnected from us. Events happening there right now cannot affect us. Events happening here right now cannot affect them. The edge is a horizon of causality. This creates a fundamental observational limit that cannot be overcome with better telescopes or more sensitive instruments. A telescope capable of detecting a single photon would still see the same boundary, because beyond it there are no photons to detect that have had time to arrive. The cosmic microwave background radiation that Planck mapped is the closest we can get to that boundary. It represents the universe approximately 380,000 years after the beginning, when it first became transparent. Before that moment, the universe was opaque. We cannot see further back in time using any form of electromagnetic radiation. Gravitational waves may provide a path beyond this barrier in principle. Gravitational waves from events in the very early universe, including the inflationary period, would not have been blocked by the opaque plasma the way light was. Detecting a gravitational wave background from inflation would give us observational access to the universe's first fractions of a second. Experiments including the planned laser interferometer space antenna are designed in part to search for this primordial signal, though detecting it represents an extreme technical challenge. What lies beyond the observable edge, beyond the causal horizon, physics cannot directly access. The universe's global geometry, whether it is spatially flat, curved, or has an unusual topology, is something we can only constrain from within our bubble. Measurements suggest the observable universe is very close to spatially flat, meaning parallel lines would stay parallel across billions of light-years, but whether this continues beyond the horizon is unknown. The patterns we detect near the boundary, the alignment anomalies in the microwave background, the cold spot, the unexpected large-scale structures, may carry imprints of physics that operated at or beyond the boundary during the inflationary epoch. That makes them potentially our only observational window into conditions that existed before the observable universe reached its current size. The edge is the limit of our map. But maps have edges because the explorers ran out of coastline to chart, not because the world ended. The universe beyond our horizon is real. We simply have no way to receive its mail. The observable universe is remarkably smooth. Regions of the cosmic microwave background on opposite sides of the sky have temperatures that match to better than 1 part in 100,000. Yet those regions are so far apart that in a universe expanding only under the influence of known forces and matter, they could never have been in contact with each other. They were too far apart, even at the moment the ancient light was emitted, to have exchanged energy and equilibrated. Something must have connected them. The theory of cosmic inflation proposes that the universe underwent an extraordinarily rapid expansion in the first tiny fraction of a second after the beginning, expanding by a factor of at least 10 to the power of 26 in a period lasting roughly 10 to the negative 32 seconds. This expansion would have taken an initial region far smaller than a proton and stretched it to a scale larger than what is currently observable. If inflation occurred, it solves the connection problem directly. The regions of the sky that appear too far apart to have communicated were before inflation stretched the universe in close contact. Their temperatures match because they were once the same region. Inflation then expanded that region to cosmic scale, preserving the uniformity. Inflation also explains why the observable universe appears spatially flat. Any initial curvature would have been diluted by the enormous expansion, much as the surface of a balloon looks flat when inflated to an enormous size. Observations confirm the flatness to high precision. The quantum fluctuations present in the initial tiny region before inflation were also stretched by the expansion, becoming the density variations that seeded all subsequent structure. The specific statistical pattern of those variations, measured in the cosmic microwave background and in the distribution of galaxies, matches the predictions of the simplest inflationary models remarkably well. Despite these successes, inflation is not a single well-defined theory. It is a framework within which hundreds of specific models exist, producing somewhat different predictions for the detailed pattern of primordial fluctuations. Distinguishing between models requires measuring the polarization of the cosmic microwave background at high precision, specifically a signal called B-mode polarization, generated by primordial gravitational waves. Several experiments are actively searching for this signal, including the South Pole Telescope and the BICEP Array in Antarctica. Inflation also raises deep questions about what the inflating field actually was and why inflation stopped. The mechanism that ended inflation is thought to have converted the energy of the inflationary field into the hot plasma of particles that became the early universe. This process, called reheating, is poorly constrained observationally. Some inflationary models predict that inflation does not end uniformly everywhere. In regions where inflation ends, a universe like ours forms. In other regions, inflation continues, spawning additional universes in a process called eternal inflation. This leads naturally to the concept of a multiverse, where our observable universe is one of an enormous or infinite number of separate expanding regions. The axis of evil alignment and the cold spot in the microwave background have both been proposed as potential imprints of unusual physics during inflation. Whether these anomalies reflect the specific model of inflation that occurred, or a collision between our inflating bubble and another, remains speculative. The data does not yet discriminate between these possibilities. What inflation gives us is a framework for why the universe looks the way it does at large scales. But the framework has internal directions, and some of those directions lead somewhere genuinely difficult to observe. If eternal inflation is correct, our observable universe is one bubble in an enormous or infinite collection of expanding regions. Each bubble nucleates when inflation ends in a local region of the inflating medium, filling with hot plasma that evolves into a universe. The bubbles are separated by regions where inflation never stopped, expanding space that can never be crossed because it grows faster than light can traverse it. This is the multiverse in its most physically motivated form. The concept arises directly from combining the mechanism of inflation with quantum mechanics. It is not a speculative add-on, but a consequence of specific inflationary dynamics that already match observations in other respects. Different bubble universes in this picture need not have the same physical laws or constants. In models based on the string theory landscape, different regions of the mathematical space describing fundamental physics correspond to different physical constants, different numbers of dimensions, different masses for particles. Each bubble universe would instantiate a different point in this landscape. Most such universes would be inhospitable to structure of any kind. The cosmological constant alone, taking a much larger value than observed in most landscape configurations, would prevent stars and galaxies from forming. These ideas are coherent as theoretical frameworks. The problem is observational access. If other bubble universes exist and are separated from ours by eternally inflating space, no signal can pass between them. They are causally disconnected in the same way that regions beyond our causal horizon are disconnected. The multiverse, in this standard form, makes no testable predictions that distinguish it from a single universe. One exception has been proposed. If two expanding bubbles happen to be close enough at nucleation to collide before the inflating medium between them fully separated them, the collision would leave a specific imprint on the cosmic microwave background. The collision would create a disc-shaped region with modified temperature and polarization patterns. Several searches for such collision signatures in the WMAP and Planck microwave background maps have been carried out. The results have not produced a confirmed detection. The cold spot has been proposed as a possible candidate, but its properties do not closely match the predictions of bubble collision models, and the supervoid explanation, while also incomplete, fits its profile better in some analyses. The multiverse remains theoretically motivated, but observationally unconfirmed. Most working cosmologists treat it as a theoretical framework worth developing, rather than a confirmed feature of reality. The distinction matters for how we interpret the anomalies at the edge of the observable universe. If they are remnants of a bubble collision, they are evidence of a larger structure beyond our horizon. If they are products of unusual inflationary dynamics within our own bubble, they are clues about the physics of the first fractions of a second. If they are statistical artifacts, they point to nothing beyond our own measurement limitations. What makes this genuinely difficult is that the universe's anomalies are real in the data, regardless of which explanation is correct. The direction they point, both physically in the sky and conceptually in theory space, converges on physics operating at or before the scale of the causal horizon. That convergence is itself informative. The edge of what we can see is also the edge of what we can test. And everything beyond it is territory where theoretical physics can venture, but observational cosmology cannot yet follow. The next chapter of this investigation is being written by instruments that are either already operating or coming online within the next few years. In July 2023, the European Space Agency launched the Euclid Space Telescope on a mission to produce the most comprehensive three-dimensional map of the universe ever attempted. Euclid is designed to observe approximately 1.5 billion galaxies across a third of the sky, spanning distances that reach back roughly 10 billion years in cosmic time. Its primary scientific targets are dark energy and dark matter, the two invisible components that together constitute roughly 95% of the universe's total energy content. Euclid will probe both through two independent methods operating simultaneously. The first method is weak gravitational lensing. As light from distant galaxies passes through the universe, it is deflected by the gravitational influence of all the matter between those galaxies and us, including dark matter. This bending distorts the apparent shapes of distant galaxies in a subtle but measurable way. By analyzing the shapes of hundreds of millions of galaxies, Euclid can reconstruct the distribution of matter in 3 dimensions, mapping dark matter structures across cosmic scales and measuring how that distribution evolved over time. The evolution of dark matter structure over cosmic history is sensitive to dark energy. If dark energy has been stronger or weaker at different epochs, it would have affected the rate at which dark matter clumped together under gravity. Euclid's lensing measurements will probe this history with precision far beyond current surveys. The second method is galaxy clustering, specifically the baryon acoustic oscillation signal measured across different cosmic epochs. By mapping the slight excess of galaxy pairs at the acoustic scale across multiple distance ranges, Euclid will trace how the universe's expansion rate changed from 10 billion years ago to the present. This expansion history directly encodes the behavior of dark energy over time, testing whether it is constant or evolving. Euclid released its first scientific images and preliminary results in 2024, demonstrating the quality of its optical and near-infrared cameras and confirming the instrument's performance matches design specifications. Full scientific results from the main survey will accumulate over the mission's planned 6-year duration. The Euclid mission is also positioned to contribute to the S8 tension. Its weak lensing measurements will determine how clumped matter is today, with independent systematics from previous surveys. If Euclid's S8 measurement falls in line with earlier lensing surveys and remains below the Planck prediction, it will strengthen the case that the tension is real and requires a physical explanation. Combined with the dark energy spectroscopic instruments' results on the ground and the James Webb Space Telescope's observations of the early universe, Euclid's data will form part of a coordinated observational campaign that will reshape cosmology's understanding of the universe's dark components within the next decade. The Vera Rubin Observatory in Chile, preparing to begin its legacy survey of space and time, will add a southern hemisphere perspective with its own weak lensing and large-scale structure measurements. When all of these datasets are combined, the statistical precision will be sufficient to either confirm the hints of evolving dark energy or rule them out decisively. The universe's edge is being mapped with increasing resolution, and the more precisely we map it, the sharper the anomalies become. Every measurement we make of the universe is made from one location. We sit in one galaxy, in one region of cosmic structure, looking outward in all directions. Our observations of the largest scales of the universe are filtered through our position in ways that cannot be fully corrected for, no matter how precise our instruments become. This fundamental limitation has a name: cosmic variance. At the very largest scales of the observable universe, the scales comparable to the observable horizon itself, there are only a finite number of independent regions to measure. On smaller scales, there are millions of galaxy clusters and billions of galaxies, and statistical averaging over large samples reliably characterizes the universe. On the very largest scales, where the patterns span a significant fraction of the observable sphere, we can only observe those patterns from one vantage point and cannot average over multiple independent realizations. In the cosmic microwave background, the largest temperature patterns, the quadrupole and octopole, are the ones most affected by cosmic variance. The standard model predicts a range of possible values for these patterns, depending on the specific random initial conditions of our particular universe. A universe that is statistically typical might still produce anomalous-looking large-scale patterns simply by chance. The low quadrupole power, the alignment anomaly, and the cold spot all live in precisely the regime most susceptible to this problem. This does not make the anomalies disappear, or make them less real in the data. It means their interpretation is genuinely ambiguous. A pattern that appears in only 3 to 5% of realizations within the standard model could be a real physical anomaly, or it could be our universe simply drawing an unusual hand from a statistically valid deck. The challenge is that we cannot go to a different location in the universe to get a second view. We cannot observe the cosmic microwave background from a galaxy a billion light-years away to check whether the same alignments appear from there. We are permanently fixed at our location in cosmic history. Cosmic variance also complicates the Hubble tension in a subtle way. If the KBC void is real and we are inside a locally underdense region, the local expansion rate is genuinely higher than the global average. A measurement made from within that void would correctly measure the local expansion rate. The question is whether the observer knows their position is unusual. Without a complete map of the local universe's density field, the correction cannot be made precisely. Future surveys, including Euclid and the Vera Rubin Observatory's Legacy Survey of Space and Time, will help by mapping the large-scale density field of the local universe in greater detail, allowing better corrections for the local environment. But the fundamental limitation of observing from one position in spacetime cannot be fully removed. This is one of the honest boundary conditions of cosmology. The universe may look systematically different from a different vantage point, and we have no way to access that alternative view. The anomalies we detect might be artifacts of our position, features of our local environment, relics of unusual primordial conditions, or genuine evidence of physics beyond the standard model. Distinguishing between these requires more data, more models, and careful reasoning about what cosmic variance allows and what it cannot explain. The one thing it does not do is make the anomalies go away. They sit in the data, real and persistent, and taken together they form a pattern that the next chapter in this investigation will lay out in its full shape. The model that has governed cosmology for the past 3 decades is called lambda cold dark matter. Lambda refers to the cosmological constant, Einstein's term for dark energy. Cold dark matter refers to a form of matter that moves slowly and clumps under gravity to build the scaffolding of the cosmic web. Together, these two components, alongside ordinary matter and radiation, form a model that successfully explains an enormous range of observations. It predicts the pattern of temperature fluctuations in the cosmic microwave background with extraordinary precision. It reproduces the baryon acoustic oscillation signal in galaxy surveys. It accounts for the large-scale structure of the cosmic web. It matches the observed abundance of galaxy clusters at various epochs. For decades, every new test produced agreement. The cracks began appearing as measurements became more precise. The Hubble tension appeared as separate measurement methods improved, to the point where their disagreement became statistically undeniable. The S8 tension emerged as weak lensing surveys grew large enough to produce reliable constraints. The alignment anomalies in the microwave background persisted through increasingly sophisticated analyses. The hints of evolving dark energy appeared as galaxy surveys reached sufficient depth. The early massive galaxies seen by Webb pushed against predictions for galaxy formation timelines. No single anomaly is definitive. Each can, with appropriate reasoning, be accommodated within the standard model or attributed to unresolved systematic errors in the measurements. But the pattern of anomalies is what is significant. Multiple independent observations, using different instruments, different physical effects, and different cosmic epochs, are all showing mild tension with the same model in overlapping directions. This situation has a precedent in the history of science. The anomalous precession of Mercury's orbit was a single small discrepancy that Newtonian gravity could not fully explain. It was small enough to be dismissed as a systematic error for decades. Einstein's general relativity resolved it by revealing that Newtonian gravity itself was an approximation of a deeper theory. The anomaly was real, and it pointed to something real. Lambda cold dark matter may be in a similar position. The tensions may be pointing toward a deeper theory that reduces to the standard model in most regimes but diverges in specific, measurable ways. That deeper theory might modify dark energy's behavior over cosmic time. It might alter the way dark matter interacts at large scales. It might require a revision to the physics of the very early universe before recombination. It might require all three. What makes the current moment scientifically significant is the combination of precision and tension. We are measuring the universe at a level of detail where the standard model's predictions are specific enough to be tested and wrong, at a level that demands explanation. A vaguer model would hide its failures in the uncertainty. Lambda cold dark matter is precise enough to be caught disagreeing with observation in multiple places at once. The disagreements are not dramatic enough to collapse the model. They are precise enough to demand a successor. Most galaxies spin. Spiral galaxies rotate about their centers, with stars, gas, and dust tracing curved paths through space. The direction of that rotation, when projected onto the sky, appears either clockwise or counterclockwise from our viewing angle. In a universe with no preferred direction, you would expect roughly equal numbers of clockwise and counterclockwise spirals in any large patch of sky. Several studies have found that this expectation may not hold. A series of analyses using large galaxy catalogs, including data from the Sloan Digital Sky Survey, examined whether the handedness of spiral galaxies is distributed symmetrically across the sky. Researchers identified the rotation direction of hundreds of thousands of spiral galaxies using automated image analysis and manual classification through citizen science projects. The question was whether the ratio of clockwise to counterclockwise spirals looks the same in all directions. Some studies reported a small but statistically significant asymmetry, with different hemispheres of the sky showing slightly different ratios of galaxy spin directions. One analysis, published in 2020, identified an asymmetry at roughly 3.8 sigma significance. Another analysis using a different dataset and method found a similar pattern. The proposed physical explanation connects to the cosmological principle. If the universe has no preferred direction, galaxy spin direction should be random and symmetric everywhere. If a preferred axis exists on cosmological scales, perhaps an axis set during inflation or carried by some unknown primordial field, galaxies near opposite ends of that axis might have a slight tendency to rotate in opposite directions, because the angular momentum of a region during galaxy formation might be influenced by the large-scale structure around it. These findings remain controversial. Different research teams using different methodologies and datasets have reached different conclusions. Systematic errors in identifying galaxy rotation directions from images, including biases in how images are oriented or processed, can produce spurious asymmetries. The automated classification methods used in large samples can introduce directional biases that are difficult to fully correct. Independent verification with clean methodology across multiple surveys is needed. The current data is suggestive but not definitive. The significance levels, while interesting, sit below what the field would require to claim a confirmed discovery. What makes this line of investigation meaningful beyond any individual study is what it is testing. The cosmological principle, the assumption that the universe has no preferred axis, is foundational. It is built into every calculation of the standard model. If the universe has a real preferred direction, even a faint one, the consequences run from galaxy formation all the way to how we interpret the Hubble constant and the microwave background anomalies. The alignment anomaly in the microwave background, the bulk flow of galaxies, the axis of the dipole in large-scale structure surveys, and now the potential asymmetry in galaxy spin are all testing the same thing. Whether they are all symptoms of the same underlying cause is one of the most interesting open questions in cosmology. And the universe's preference for direction, if it is real, has a cousin in an even more extreme structural asymmetry found in one of the most energetic events in the cosmos. Gamma-ray bursts are the most luminous explosions observed in the universe. They occur when massive stars collapse into neutron stars or black holes, or when two neutron stars spiral together and merge. The energy released in seconds can outshine entire galaxies. More importantly for cosmological mapping, they are detectable across enormous distances, making them one of the few phenomena visible across a significant fraction of the observable universe's depths. Their spatial distribution has produced several surprises. When researchers analyzed the positions of gamma-ray bursts in the sky across a catalogue of hundreds of events, they found evidence for clustering at scales larger than the standard model's end of greatness predicts. Individual structures appeared in these distributions at scales of several billion light-years. The Hercules Corona Borealis Great Wall, identified in 2014, was the most dramatic example, but earlier analyses had already flagged anomalous clustering. A structure called the Claus-Campesano Large Quasar Group, identified in the 1990s, spans roughly 2 billion light-years. The giant arc, identified in 2021 using quasar absorption systems as tracers, stretches approximately 3.3 billion light-years. Each of these structures sits above or near the theoretical limit for what gravity can assemble in the age of the universe. The giant arc was identified by a team using data from the Sloan Digital Sky Survey. They found an alignment of quasar absorption features arranged in an arc across the sky that, at the measured distances, corresponds to a physical scale of roughly 3.3 billion light-years. The structure's existence at this scale is difficult to reconcile with the standard model's prediction that the universe should be statistically uniform above approximately 1.2 billion light-years. Critics note that identifying large structures from projected sky positions involves assumptions about whether the galaxies or quasars in question form a physically connected entity or simply appear aligned from our viewing angle. A chance alignment of objects at slightly different distances can mimic a large structure in projection. Careful analysis requires measuring the three-dimensional positions of all members to confirm physical association. The statistical significance of these structures, and whether they represent genuine violations of the cosmological principle, or statistically improbable but possible fluctuations within it, is actively debated. What is consistent across multiple independent findings is that large-scale structure surveys keep finding features at or above the scale where the universe was supposed to become featureless. The end of greatness has not cleanly ended. Structure persists at scales that test the boundaries of what the standard model allows, and the instruments being built to settle this question will either confirm that the universe is as uniform as the model requires, or reveal that the largest structures in existence require physics we have not yet identified. On a mountain in the Chilean Andes, a telescope unlike any previously built is preparing to begin a decade-long survey of the southern sky. The Vera Rubin Observatory, named for the astronomer whose work on galaxy rotation curves helped establish the reality of dark matter, houses a camera with a field of view so wide it can photograph an area of sky 40 times larger than the full moon in a single exposure. Its primary mirror measures 27 feet across. Every 3 nights, it will photograph the entire accessible southern sky. This program, called the Legacy Survey of Space and Time, will run for 10 years and generate approximately 20 terabytes of data every night. It will catalog tens of billions of astronomical objects, tracking how they change over time. It will detect approximately 10 million supernovae over its operational lifetime, revolutionizing the statistical precision of supernova-based distance measurements and providing a massive independent dataset for measuring the Hubble constant. The survey's dark energy science will come from multiple channels simultaneously. The supernova sample alone will constrain the dark energy equation of state with unprecedented statistical power. Weak gravitational lensing measurements from billions of galaxy shapes will probe the distribution of dark matter and the growth of structure. Galaxy clustering across the southern sky will measure the baryon acoustic oscillation signal at multiple cosmic epochs. The combination of these independent probes from a single survey will cross-check systematic errors in ways that no previous instrument could achieve. Rubin will also contribute to the S8 tension directly. Its weak lensing measurements will be the most precise from any ground-based survey. If the matter-power spectrum measured by Rubin continues to fall below the Planck prediction, the tension will be confirmed with enough statistical weight to be undeniable. If Rubin's measurement lands closer to the Planck value, it will suggest that earlier lensing surveys carried systematic errors that inflated the apparent discrepancy. The Legacy Survey of Space and Time will also map the solar system more comprehensively than any previous sky survey, discovering hundreds of thousands of new objects in the outer solar system. This is scientifically separate from the cosmological program, but demonstrates the breadth of a single instrument capable of addressing questions ranging from our local neighborhood to the edge of the observable universe. First light for the Rubin Observatory's science operations is planned for 2025, with the full survey cadence ramping up over subsequent months. The first few years of data will begin addressing the cosmological tensions with early results. By the mid-2030s, the complete dataset will be one of the most comprehensive observational records of the universe ever assembled. The anomalies at the edge of the universe will either resolve under this scrutiny or sharpen into something undeniable. Either outcome advances our understanding. The universe does not mislead, it simply gives us data, and the data so far suggests the map we built has edges we had not anticipated. In September 2015, the Laser Interferometer Gravitational Wave Observatory detected gravitational waves for the first time in history. The signal came from 2 merging black holes roughly 1.3 billion light-years away, each roughly 30 times the mass of our star. The detection opened a new way of observing the universe, one that does not rely on light at all. Gravitational waves are ripples in space-time itself, generated by accelerating masses. They travel at the speed of light and pass through matter without being absorbed, scattered, or otherwise altered. This makes them ideal messengers from some of the most extreme events in the cosmos. Their cosmological significance extends beyond simply detecting mergers. When 2 neutron stars spiral together and merge, they produce both gravitational waves and a burst of light across multiple wavelengths. This combination is called a multi-messenger event. The gravitational wave signal encodes the intrinsic brightness of the event, essentially making it a standard siren analogous to the standard candle roll of Type 1a supernovae. By comparing the intrinsic brightness from the gravitational wave signal with the observed brightness from the electromagnetic emission, astronomers can measure the distance to the merger without needing a calibration chain of intermediate distance markers. In 2017, the merger of 2 neutron stars was detected by the Laser Interferometer Gravitational Wave Observatory and Virgo simultaneously with gamma-ray and optical light. This event provided the first gravitational wave-based measurement of the Hubble constant, giving a value in the high 60s range, with an uncertainty too large to discriminate between the competing measurements from the Planck and supernova methods. As more multi-messenger events accumulate, the statistical uncertainty will shrink. Estimates suggest that roughly 50 well-characterized neutron star merger events would bring the gravitational wave Hubble constant measurement to a precision comparable to current electromagnetic methods. If the gravitational wave measurement converges on either the lower or higher value, it will provide an independent verdict on which of the two competing measurements is correct. The planned Laser Interferometer Space Antenna, a space-based gravitational wave detector, would extend this reach enormously. It is designed to detect lower-frequency gravitational waves than the ground-based detectors can access, including waves from merging supermassive black holes at cosmological distances. These massive events are detectable across much of the observable universe, providing standard siren measurements at scales far beyond what ground-based instruments can reach. A primordial gravitational wave background from inflation, if detectable, would carry information about the earliest moments of the universe. The amplitude of primordial gravitational waves encodes the energy scale of inflation. Detecting it would be one of the most significant observations in the history of cosmology, providing a direct measurement of physics operating at energy scales a trillion times beyond what particle accelerators can access. Gravitational wave cosmology is in its infancy. Each detection adds to a dataset that will grow substantially over the coming decades. At the edge of what we can observe, gravitational waves offer a path around the limitations of electromagnetic astronomy, a way to read the universe in a different language. And what that language might eventually tell us about the farthest reaches of space points toward the most fundamental question this investigation has been building toward. Lay out every major anomaly discussed in this investigation and look for what they have in common. The alignment in the cosmic microwave background, where the largest temperature patterns point in a specific direction rather than orienting randomly. The axis associated with that alignment roughly matches the direction of Earth's orbit around the star and the direction of our motion through the background radiation itself. The bulk flow of galaxies across hundreds of millions of light years, converging toward the Great Attractor and the Shapley supercluster in a specific region of the sky. The dipole repeller pushing from the opposite direction. The cold spot in the microwave background, sitting in a region geometrically related to the alignment axis. The potential asymmetry in galaxy spin directions, with different hemispheres showing slightly different handedness. The gamma-ray burst clustering that produces apparent large-scale structures, aligned across specific regions of the sky. Taken individually, each anomaly has a plausible conventional explanation, or sits at a statistical level where random chance cannot be excluded. Taken together, the pattern is harder to dismiss. Multiple independent measurements, using different physical effects, different instruments, and different cosmic distances, are pointing toward a universe that is not equally featureless in all directions. This is precisely what the cosmological principle forbids. The principle states that the universe should have no preferred direction and no preferred location. It is the foundation on which every calculation in the standard model rests. If the universe genuinely has a faint preferred axis, every calculation that assumes otherwise carries a systematic error, and those errors compound across the entire edifice of modern cosmology. The scientific response to this situation has been careful. No major research group has abandoned the cosmological principle. The anomalies are real in the data, but none has reached the level of statistical certainty that would force a fundamental revision to the framework. The honest position is that the evidence is suggestive, the pattern is real, and the explanation remains open. Several categories of explanation remain under active investigation. The alignment could reflect the structure of the universe at scales near the causal horizon, imprinted by inflationary physics that broke perfect isotropy. The bulk flows could be the result of structures we have not yet fully mapped beyond the regions our surveys reach. The galaxy spin asymmetry could be a measurement artifact that disappears under more rigorous methodology. The cold spot could eventually yield to a combination of the supervoid and statistical fluctuation explanations. Or the pattern could be telling us something real about the universe's global structure, something that only becomes visible when you combine all the measurements and look at where they collectively point. That something could be a relic of the initial conditions that set the universe in motion, a faint signature of the era before the observable universe reached its current size. If inflation was slightly asymmetric, if the field driving it had a preferred direction, even temporarily, that direction could have been stretched across the observable universe and frozen into the large-scale patterns we now detect. The evidence has not solved the mystery, but it has made the mystery specific enough to test. And the final question this investigation has been building toward is the one that puts everything in its largest possible frame. The observable universe spans approximately 90 to 3 billion light-years. It contains an estimated 2 trillion galaxies. Every piece of knowledge in human cosmology was extracted from within this sphere, and this sphere may be a vanishingly small fraction of a vastly larger whole. Several independent lines of reasoning suggest the universe extends far beyond what we can observe. The first comes from geometry. Measurements of the cosmic microwave background show the universe is spatially flat to very high precision, with a curvature consistent with zero within current measurement uncertainties. A finite universe with a specific size and shape would produce a characteristic signature in the microwave background, including patterns that wrap around the sky in specific ways. No such pattern has been detected. The most constraining analyses suggest that if the universe has a finite size, it must be much larger than the observable sphere, at minimum several hundred times larger. The second comes from inflation. If inflation occurred, it expanded the universe by an enormous factor. The universe before inflation may have been small enough to be fully causally connected, but after inflation, the total volume of the universe would dwarf the observable portion. The observable universe represents the patch that has been causally accessible since the end of inflation. Everything beyond our horizon is the rest of an inflated volume that may be effectively infinite, depending on the inflationary model. The third comes from the statistical analysis of the microwave background's largest patterns. The low quadrupole power, the anomalously weak signal at the largest scales, could in principle be explained if the universe has a size comparable to, or only modestly larger than, the observable sphere. In that case, the largest possible modes of fluctuation would be suppressed by the finite volume. But this interpretation requires a universe fine-tuned to be just large enough to explain the suppression, which most cosmologists find less compelling than other explanations. If the universe is much larger than the observable sphere, regions beyond our horizon are real but permanently inaccessible. They exist in the same space-time as us. The laws of physics presumably apply there. Matter, energy, and possibly galaxies exist there. Events happen there, but no information from those regions has reached us, and none ever will, because the expansion of space between here and there grows faster than any signal can travel. This raises a genuinely difficult epistemological question. Science operates by testing claims against evidence. A claim about regions of the universe that are permanently beyond any possible observation cannot be tested in the traditional sense. Whether those regions exist, whether the laws of physics are the same there, whether structure formed there in the same way, are questions that may never yield to empirical investigation in any direct form. Some of the anomalies at the edge of our observable universe may be our only indirect window into conditions that extend beyond our horizon. The alignment patterns, the low quadrupole, the large-scale asymmetries could all carry information about the universe's global structure at scales larger than our causal horizon. They are not proof of anything beyond the horizon, but they are the data that sits closest to that boundary. The universe almost certainly extends beyond what we can see. How far, what it looks like, and whether it is anything like our observable patch, is knowledge the cosmos may be keeping permanently out of reach. Every anomaly in this investigation was identified through measurement. Every tension in the standard model was exposed by instruments precise enough to find where predictions fail. The universe did not hide these signals. We simply needed the technology and the time to hear them clearly. The next decade of cosmological observation will be the most data-rich in the history of the field. The Dark Energy Spectroscopic Instrument is midway through a 5-year survey that will map tens of millions of galaxies and quasars across a substantial fraction of the observable universe. Its second-year data release will test whether the hint of evolving dark energy seen in the first-year results grows or fades. By the survey's end, the dark energy equation of state will be constrained with a precision that either confirms the Standard Model's cosmological constant or demands something beyond it. The Vera Rubin Observatory's Legacy Survey of Space and Time will image the southern sky repeatedly for 10 years, accumulating a dataset of unprecedented depth and breadth. Its supernova sample, weak lensing maps, and baryon acoustic oscillation measurements will converge on the Hubble and S8 tensions, with statistical power sufficient to reach definitive conclusions about whether the tensions require new physics or reflect correctable systematic errors. The Euclid Space Telescope will spend 6 years mapping the shapes and positions of 1.5 billion galaxies across a third of the sky, providing its own independent view of dark energy's history and dark matter's distribution. Combined with Rubin's ground-based data, the joint dataset will be the most powerful probe of the universe's dark components ever assembled. The James Webb Space Telescope will continue observing the earliest galaxies, refining mass estimates through spectroscopy, and building a picture of how galaxies formed across the universe's first billion years. Its contributions to the Hubble tension will continue as it measures more Cepheid variables and probes the distance ladder with greater precision. Gravitational wave observatories will accumulate more multi-messenger events, building toward an independent Hubble constant measurement that bypasses the electromagnetic distance ladder entirely. The Laser Interferometer Space Antenna, if approved and built on its current timeline, will extend gravitational wave cosmology to the universe's most massive mergers across billions of light years. The South Pole Telescope, the Simons Observatory, and the BICEP Array are searching for the primordial gravitational wave signal imprinted on the polarization of the cosmic microwave background. A detection would confirm inflation and measure its energy scale. A continued non-detection will constrain which inflationary models remain viable. The anomalies will either sharpen into discoveries or dissolve into better measurements. The Hubble tension will resolve toward one of the competing values, or reveal that neither is correct and a deeper model is required. The alignment anomalies will either strengthen with more precise data or be traced to instrumental systematics. The hints of evolving dark energy will either grow into a confirmed detection or be absorbed into the statistical noise of a standard model that holds. None of these outcomes is certain. All of them are worth knowing. The edge of the observable universe is not a passive backdrop. It is a surface of information, a boundary where light from the oldest epochs of cosmic time is still arriving, still carrying data about what happened before galaxies existed, before atoms formed, before the universe became transparent. Everything we have discovered about the large-scale structure, the dark components, the anomalies, and the tensions in our model came from that arriving light and from the structures that ancient light eventually built. The universe is not finished speaking. We are still learning how to listen.